Hello students, I am Professor NAVNEET KAUR from EC Department, SIRT College. Today I will be taking lecture on the subject Digital Signal Processing. The topic which I will be discussing here is Discrete Fourier Transform. Now, first we will discuss the concept of the sampling. Now, initially when we have continuous time signals which have value of the function at every value of the time, we do the sampling of the continuous time signal to change it into discrete time signal. Now, in sampling, we calculate the value of the continuous signal at discrete points. Quantization determines the value of each sample value. Now here we can see the sampling of the periodic function which is represented by xt. Now xt is the continuous time signal and we want to generate the sampled version of this continuous time signal, say yt. Now yt is represented by xst. S represents the sampled version of the xt. Now xst is given by an expression summation k is equal to minus infinity to infinity xt into delta t minus kt. Now, according to the sampling property of the unit impulse function, when any unit impulse function is located at the time instant kt, then the other time dependent function here xt is also evaluated at the point at which this unit impulse function is located. So since here delta t is located at kt, xt will also be evaluated at the point kt. So here we will have xkt delta t minus kt. Now we want to change this time domain sample signal into its frequency domain. Say omega is the sampling frequency, then according to the convolution property, xs omega is given by 1 upon 2 pi x omega in convolution with the convolution of delta t minus kt. And this delta t minus kt is represented by its frequency domain representation omega s summation delta omega minus k omega s. Now, when any function is convolved with the shifted unit impulse function, it results in the shifted function itself. So here we will write omega s upon 2 pi summation x, which is the function x, omega minus k omega s. Now omega s upon 2 pi is given by 1 upon t, where t is the sampling time period. Now here we can see that when we plot this spectrum xs omega, here to avoid the overlapping of the neighboring functions, neighboring spectrums, here we will see that omega s should be greater than the 2 omega b. So according to the sampling theory, the sampling frequency should always be greater than 2 omega b, where omega b is the maximum frequency component of the message signal. Now, in continuous time Fourier transform, when the signal is sampled, it is represented as summation n is equal to minus infinity to infinity x n t e to the power minus jn omega t. Now here we can represent x n t, which is the value of the function at nth time interval t. It can be represented as only as x bracket n. Now this analog frequency ohm is given by W into T. So discrete time Fourier transform x ohms is represented by summation n is equal to minus infinity to infinity xn e to the power minus j ohm n. Here we have represented ohm into W into T by ohms. So the inverse representation, that means its time domain representation, is given by xn is equal to 1 upon 2 pi integration of x ohms e to the power j ohm n d ohms. So the discrete time Fourier transform is given by this expression summation xn e to the power minus j ohm n, and the inverse discrete time Fourier transform xn is given by an expression 1 upon 2 pi integration of x ohms e to the power j ohm n d ohms. So here we have given the both expressions Dtft and its inverse Dtft. So there are few characteristics of the Dtft which I will discuss here. The first important characteristic is that Dtft is periodic in frequency with a period of 2 pi. Because here we can see that e to the power j ohm, when it is given as g ohm e to the power j ohm plus 2 pi, it will be represented at e to the power j ohm into e to the power j2 pi. Now we all know that e to the power j2 pi is given as cos 2 pi plus j sine 2 pi, which gives the value 1. So it will be given as e to the power j ohm. So therefore, using this property of the exponential function, we can conclude that this Dtft x ohm will have the same value after an interval of 2 pi, 4 pi and so on. So we can say that Dtft is periodic in frequency with a period of 2 pi. Dtft allows us to find the spectrum of the discrete signal. Now, next we will define the discrete Fourier transform. The first important thing which we should know about the Dtft, that Dtft is periodic in nature with period 2 pi, as well as it is continuous in nature. Continuous means that it will have a continuous spectrum in the frequency domain. Now, this continuous spectrum cannot be given to the discrete signal processors because it is continuous in nature. So, we want to change it into the spectrum which is discrete in nature. Now, for that, we have to do the sampling of the spectrum which is represented by Dtft. So, this spectrum is represented by xk, which will be represented by x2 pi k upon n. That means here we have replaced ohm as 2 pi k upon n, where k is having values 0 to n minus 1. That means we are taking total n number of samples of the continuous spectrum which is represented by Dtft. So here now we will have a spectrum which will have n distinct sample frequencies of x ohm. Now here the points are spaced at an interval of 2 pi by n. Thus the resolution of the samples of the frequency spectrum is 2 pi by n. Now here we will see that xk, which is actually the discrete Fourier transform, is given by x ohm, which is Dtft, when we will take the value of ohm at 2 pi k upon n, where k is represented by the values 0, 1 until n minus 1. So here we will see when we will represent this x ohm, which is Dtft, by its formula, that is summation n is equal to 0 to n minus 1 xn e to the power minus j ohm n, and we will take the value of ohm at discrete instance 2 pi k upon n. So here we will get a new formula xn e to the power minus j 2 pi k small n upon capital N. So this is the expression for our Dft of the discrete time signal, where Dft is the discrete Fourier transform. Now, if I want to represent xk in the terms of the twiddle factor Wn, where Wn is represented by e to the power minus j 2 pi by n, we can write xk as summation n is equal to 0 to n minus 1 xn Wn raised to power kn, where k is given by the values 0, 1 and so on till n minus 1. Now here we can see where we have represented w as n as e to the power minus j 2 pi by n. So we are writing the Dft expression in terms of twiddle factor here. Now here we can see both the domain representation of any signal. Here we have this finite sample time domain signal xn, which is having samples from 0 to n. Now when it is represented by in the frequency domain, it is given by the Dft formula xk here, which is given by n is equal to 0 to n minus 1 xn wn kn. Now here we can see the frequency domain representation, which is given by xk, and here we are having samples from 0 to n. Here the samples are shown from 0 to n because the DFT spectrum will repeat itself after every n samples. That means after n sample, the same spectrum will repeat. So here in brief, we can see that the discrete Fourier transform is obtained by uniform sampling x omega, which is Dtft, on the omega axis. And the definition of DFT is given by the expression which we have already discussed in the previous slides. Here we can see that the notation of the twiddle factor is also used, which is given by the e to the power minus j 2 pi by n. So our formula is written in the terms of the twiddle factor. The inverse discrete Fourier transform is also discussed in previous slides, which is given as xn 1 upon n summation k is equal to 0 to n minus 1 xk wn raised to power minus kn, where n is having value from 0 to n minus 1. Now, next we will discuss the properties of the DFT. Now, the first property is linearity property. Now, according to the linearity property, now when we are having two discrete time signal x1n, which is having DFT x1k, and x2n, which is having DFT x2k, then in that case, a x1n plus b x2n, where a and b are two constants, the DFT of this sum is given by ax1k plus bx2k. That means here we can say that it satisfies the superposition principle. Similarly, the second property is given by the shift of the sequence. That means if we shift the time domain signals by m units, in that case, our frequency domain representation xk is represented by an exponential term which will be having frequency m, which here m are the units by which this time domain signal is sampled. Here we are using xn minus m mod n. It is represented by n minus m plus r into n, where r is any integer. This is used to represent any periodic signal. When this integer r is chosen, then we can say that the n minus m plus r should lie between 0 to n minus 1. Here we can see that when we are having any sequence xn, which is having samples from 0 to n, we can generate another sequence which is the periodic version of this sequence xn. So here we can see that x cap n is the periodic version of xn, where the samples from 0 to n are repeating itself. Now, if I will shift this x cap n by 2 units, or I'll advance this sequence by 2 units, I will get a new sequence, say x1 cap n. Now, if I will truncate this sequence from 0 to n, that means I'll ignore all the samples after n and before 0, I'll get a new sequence x1n, which is given by x1 cap n when I will evaluate the samples from 0 to n minus 1. Now, the next property is circular convolution. Now, according to this circular convolution, if we are having two sequences x1n and x2n, which are having DFTs x1k and x2k respectively. Now, if I'll do circular convolution in time domain, then in frequency domain, we can say that their respective DFTs are getting multiplied, x1k into x2k. The circular convolution formula is represented by summation m is equal to 0 to n minus 1, x1m, x2n minus m mod n, where this symbol is representing circular convolution operator. Now here we can see on this slide more properties of the DFTs. Here we can see the multiplication property, which says that if we multiply the time domain signals, their frequency domain representation is getting convolved. Similarly, conjugation property, that if we'll take conjugation of xn and we will find out its DFT, it is represented by x conjugate minus k. Now here we have another property. If I want to find out DFT of real part of xn, it is represented by half xkn plus x conjugate minus kn. Similarly, if I want to find out DFT of j imaginary part of xn, it is given by half xk minus x conjugate minus k. Similarly, other properties can also be seen on this slides. But the main properties which are used for DFT are already discussed in previous slides. Now, next we will see the basic examples of the DFT. Now, the first is when I want to find out the DFT of xn is equal to 1, where it is having one value from for n is equal to 0, and for 0 it is having value 0 from when n is from 1 to 7. Now, since here we are taking samples n is equal to 0 to 7, we will take capital N as 8. Now, according to the formula of DFT xk, which is given by n is equal to 0 to 7, xn, wn, kn. 7 is used because here we use n minus 1. Now, I will replace this xn by delta n, because when we are having xn as when at n is equal to 0, it is given by delta n, wn, kn. Now, when we evaluate this summation, I will get value 1. So, I can say that the DFT of delta n is given by 1. Now, next thing, I want to find out DFT of signal yn, which is represented by delta n minus 2, and the value of capital N is 8. Now here we can see that I am using the formula for DFT. So here in place of function, I'll take delta n minus 2. Now, according to the sampling property of the unit impulse function, if my unit impulse function is located at n is equal to 2, then the other function is also evaluated at n is equal to 2. So here we can see that Wn, here k into n will be taken as 2, so Wn 2k. Now I will be left with delta n minus 2 with summation. We know that the area under the unit impulse function is always unity, so we will be left with only Wn 2k. Now, substituting the value of Wn, which is given by e to the power minus j 2 pi by n, here the numerator and denominator terms will get cancelled. So I'll get e to the power minus j pi k by 2. Now, if I'll evaluate this, I'll get minus j raised to power k. Now, here we can see the correlation between the time shifting property and the solution of this example. According to time shifting property, if any signal xn is shifted by units n naught, then in frequency domain representation, I'll get xk wn n naught k. Similarly, here we can use that the delta n was having DFT 1. When I am shifting it by 2 units, I'll get 1 into wn raised to power 2k. So here we can see we get the same answer, which relates with the time shifting property of the DFT. Now here we can see one more example where we want to find out DFT of xn is equal to delta n plus 2 delta n minus 1 plus 3 delta n minus 2 plus delta n minus 3. And here we are taking capital N is equal to 4. Now using the shifting property of the DFT, we can see the answer. Here delta n will have DFT 1, 2 delta n minus 1, 2 W4k, because here we are using capital N as 4. Similarly, 3 delta n minus 2 will have 3 W4 2k, and delta n minus 3 is W4 3k. Here we are using two properties of the DFT. One is the linearity property and another is the shifting property of the DFT. So when we will evaluate W4k, W4 2k and W4 3k, we will get the respective answers e to the power minus j 2 pi k by 2, e to the power minus j pi k, e to the power minus j 3 pi k by 2. Now this is all for today's lecture. Thank you.